Yeah, in today's lecture, I would like to talk about two works that looks to bridge something that is impossible to be together. Yeah. First, it is used the static model to do the dynamic task. That is the 3D domain work. And in our second project, we are trying to use the classifier to do the detection task. Yeah. So in a short, today I would like to talk about something, in which we can put some seemingly irrelevant things together. Yeah. Well, let's first look at our outline today. Yeah. In each of the project, we will talk about the task, motivation, and main idea, and our methods, as well as the experimental details. First, let's look at the first one. How we use the static classifiers for dynamic point cloud models. It's the 3D work. Let's see. First, we would like to talk about our task. In this task, we would like to classify a point cloud sequence. This concept is similar to the so-called video classification in the 2D area. In this problem, the input is a sequence of the point cloud frames, and there is the analogy to this 2D videos. We have the video as the input, but in the 3D domain, this is the point cloud sequence. But in essence, they are alike. And given this input, our model is required to output the sequence level categories of such as gestures, actions, events, and so forth. Then an intuitive explanation should be like we put the sequence or the video or this point cloud video into the model, and it should output the sequence level labels, like in this, or maybe this video is kicking a football. The model will need to output this category. And this is what we are trying to do. And let's look at our motivation and main idea. We would like to extend the static models to classify this dynamic sequence. Similarly, in the 2D domain, we are some works have tried to use the image model, or try to extend the image model to classify the 2D videos. One typical work in the 2D domain is the so-called two-stream network, in which they can use one stream to model the static video appearance, and the other streams is used to model the dynamic or the temporal information of the video. And why do we want to use the static model to do the dynamic task? That is because the static model the static models have their own merits. Like from this figure, we know that they have a very small computational overhead, like they have a small number of loops, and they have a small number of parameters. However, if we directly use the static model in this dynamic task, we will have the poor performance like this. We have a very low accuracy. Yeah, let's look at this y-axis. Yeah, we only have we have the lowest accuracy here. Yeah, compare with other static model or some other else. Yeah, but if we can extend this model to the dynamic task, we will get the we will have the high accuracy, yeah, by improving these static models. But simultaneously, we can preserve all of the advantages of this static model, such as low computational complexity and few extra parameters, and more importantly, because typically the static models, we have more static, mature static models than the dynamic models. So as long as we have this static model, we can do minor network surgery and use this to extend this to many types of the static backbones. That is our motivation. In summary, we would like to get the big gain from the performance or the computational or something else, but we would like, but simultaneously we would like to avoid the pain of this very painful computational process. Yeah, and let's look at our main idea. What are we trying to implement this? And to make the model have low computational complexity and few extra parameters, we mainly make two improvements to make the model more lightweight and efficient. Let's look at the left one. This is the typical two-stream models, or the vanilla two-stream models, in which we typically have two steps to improve the to extend the static models. The first steps, we need to use a model to extract the pointwise syncflow information. That is to estimate the optical flow in the 2D images. We're trying to use a model to calculate the low-level point-to-point correspondences across different frames. And yeah, And after that, after we have the syncflow, yeah, although that is a painful process. However, we have another painful process. We need to use a separate model to come to take this as the input and then output the result or output the classification from this temporal information. And then by aggregating these two streams, we have the final output. And in our framework, we're trying to achieve the similar goal in another way. We are trying to reduce these two processes into one, and by removing the explicit point-wise correspondences estimation, yeah, we remove them here, and by removing the standalone temporal branch like the orange ones, we indeed achieve a lightweight and efficient framework in this static to dynamic task. Yeah, and let's look at our next slide. This is talking about our methodology. The first one would be, how do we remove the explicit point-wise correspondences process? That is very simple, actually. That is not simple, yeah, but the concept behind it is quite simple. Yeah, we get inspiration from the traditional point cloud registration. Instead, checking of the point-wise correspondences like this gray arrows here. Yeah, we don't do this. Yeah, instead, it seems feasible to model this as a local space-time surface like the gray by the gray plane like this. Yeah, since the local movement local movements have some consistency in a very small area like this, although they are point-to-point correspondences. However, they have this almost the same movement in this area. So we can use a consistent plane or the consistent so-called space-time surface to model its dynamic information. Yeah, that is our key idea. And mathematically, we can use this tangent plane equation, which is defined as the xj here is the so-called space-time neighbors. Yeah, that is the first three blue points, the second three green points, and these purple points together. We use we use a surface equation trying to fit these points well. And by doing this, yeah, we use the least square equation or the least square solution to get the optimal coefficient. And then after fitting this, or after obtaining the tangent plane equation, we can get the normal of this plane. Yeah, that is the red and I here. And this, and we can use these vectors as the features to model or to describe the movement or the temporal information. Yeah, and by doing this, we remove the explicit pointwise correspondence estimation. And this is the number one. That is the first step to reduce the computational complexity. And second, let's look at.
I have a question. The previous slide. So there are a lot of characters here. What does each character represent?
Yeah, AB is the
tangent plane.
Yeah, the coefficient of this tangent plane equation. Yeah, that is the coefficient we don't know. Yeah, but here, yeah, the xj in this in this figure, yeah, it can be viewed as the we have how many points lie on this surface, or this is the coordinate of these points. Yeah.
So x is a three-dimensional coordinate.
In the original part, it is the three-dimensional coordinates. Yeah, but we are trying, but as we can see here, we are trying to use in the high-dimensional feature space. Yeah, but we can imagine, yeah, that it is actually the same in the high-dimensional feature space. We have the high-dimensional hyperplane, yeah, instead of the plane. Yeah. Yeah, but
this is a point cloud, so there's 3 dimensions just for the location of the point, but you're also using time as another dimension. So shouldn't it be 4-dimensional, like in the basic case, not in the high?
Actually, it should be the 4-dimensional cases. Yeah, because we can see here, yeah, we even in the 2D cases we have x, y plus the t dimension. Yeah. So in the 3D point cloud, it is a 4D plane. Yeah.
Okay.
Higher dimensional cases, it is the higher dimensional plus 1.
And what is tau?
Sorry.
Tau, the character above the x on the.
Yeah.
What is it?
Do you mean which one? Which character?
There is one on the right side of the equation and one above the xj, just above it.
Oh yeah. J. Yeah. Let's first look at this tau. The tau should be the t like this. For example, in the t-1 frame, this tau is equal to t-1. That is just a sign to mark their temporal location and their space. Yeah, the J means their spatial location. Yeah, and the tau here means the temporal location. That is why we call this the space-time. So that is the space-time points here. Yeah, or the space-time coordinates. Yeah.
And why does this equation needs to be equal tau? Why does it need to be equal time?
Yeah. We can see here. For example, we can. Yeah. Let's first imagine this. This is the t domain, or we can see for the single value of for a single value across this t is the tau here. And we can see for each point on the tau frame or on the t frame, actually the value of this t axis is the tau. Yeah. And for example, is on this frame the point lies on the place of which the t value is t minus 1, and in this we have the tau of t here, and on the this should be the plus on
plus
the
1
t plus 1 frame we have the tau equals t plus 1 here. And so if we want to use a plane to fit this in the 4D or this figure is the 3D cases, we should use this ax, it should be the xy domain, when it plugs some certain value, that is the tau, that is a point on this axis.
But we said that x is 4 coordinates, one of them is time. So if x is 4 coordinates, one of them is time, that tau should be 0, no? On the right side of the equation, because we already have the time encoded within x.
That's not the 0, because the t is a value. For example, in the frame number 1, the t should be 1, and in the frame number 2, that is the 2, but maybe in the frame 0, it can be the 0, but it's not. But it's but if it would not affect too much of the normal calculation, whether it's 0 or some else number or not, their normals should be almost the same, because as long as the shape of this plane or this tangent plane is unchanged, the normals should be the same.
But if x is 4 coordinates, so there's x, y, z, and tau. This is the coordinates for x. That tau coordinate is already taking care of tau. Do we have to have the tau on the right side of the equation also?
The only difference is that the x here is 2D, a 2D vector, and when we have the 4D cases, the x here is a 3D vector.
So it's 3-dimensional, not 4-dimensional. It's just 3-dimensional in the 3D case.
We only have the 2D in the space. Because we cannot show the cases in 4D. It's very hard to plot.
So basically, x is, when we're looking at a 3D case, x has 3 dimensions. Just the spatial dimensions, no time dimension within x, right? Okay, this makes more sense. Okay. Another, what is P?
B, the B here.
P like Papa, not the B is, of course, that's the
where is the P?
Forgot in English. For each Pj tau in NIT, tangent plane equation on the left side of it.
The P means a point. It means a
for
point.
Each point.
We can take for example xit means the coordinates of the point P.
Okay. Okay. NIT, that's the points. Okay. Now another question, how do we pick the points that define the surface?
That is an interesting question. Conceptually, it is the so-called space-time neighbors. In this, they have a very close. They are close to each other in the spatial domain as well as the temporal domain, and that is the space-time neighbors. But in practice, we take the same strategy of the sampling as well as the the static convolution, the static point cloud convolutions. Like this, for example, in each convolution, they we see a small area near the point, near a certain point. Yeah, we can imagine like this is like the 2D cases. Yeah. Also, we have the similar process on the 3D cases. Yeah, they have very they have the one convolution can get its neighbors in the very small radius range. Yeah, and by doing this, we can sample and sample some neighbors. Yeah.
And I, the notation I, what does it mean?
Yeah,
like NIT.
Yeah, we just would like to separate the concept between one certain point and its neighbors. And in case, I means the
that specific point.
Yeah, and it means it means its neighbors. Yeah, but actually that is just that is just a letter to show the spatial order, or to just ID. ID in this points domain, or the coordinate domain. Yeah, so it doesn't vary. It doesn't matter too much in this in the real implementation. Yeah, but for the mathematics, yeah, it's a useful mark to
of course.
Yeah.
So if I repeat, just like so everybody watching this, I means we select a specific point of the point cloud in the 3D space. That means X, Y, Z. And then N of I in time t means that in time t, we selected N points close to point I.
Yeah.
Right? The selection could be based on convolution or something else, doesn't matter. And we go over all these points together along with the time axis. They define a surface.
Yeah.
And we search for the normal for that surface. Okay. That all the points are represented in three-dimensional space, in basically 3D points, as X, where J is the specific point which is adjacent to point I. Tau is the time where we're looking for this point's location, and we're looking for the normal that is 90 degrees to the entire surface in point T, in time T for point I specifically. Okay.
Yeah. Perfect. Yeah. Yes. Thank you for your clarity. Crystal clear. Yeah.
Sure. I'm putting myself on mute again.
Yeah. Let's go to the second step. In the second step, we are trying to remove the so-called standalone temporal branch. We're doing this by generalizing the solver of this iterative normal refinement. Yeah, because in this slide, we only propose the target or the objective of this equation. But how we can get the optimal A and B, or the optimal N in the feature space, and that is actually an optimization process. In the traditional work, we have the so-called solver of iterative normal refinement, in which the model is trying to get the best or the optimal value of a normal by removing the noises from some irrelevant points. And from the 3D, and from this 3D physical space, it is non-differentiable process, and we're trying to extend this to the high-dimensional feature space and make it differentiable. Yeah, that is our main motivation here. And in practice, this solver rough iterative normal refinement consists of two typical processes. One is the so-called normal estimation. We are trying to use like some MSE or something else to fit this equation. And second, we would like to do the so-called neighbor weighting like this to calculate the weight of one weight for one point like here. For example, when we have a small weight of a point, we will attach less importance to this point when we calculate the surveys. And by doing this, the noises or the irrelevant points can be reduced. And that is a process in the 3D in the typical 3D space, and we would like to generalize this to the convolutional or to the high dimensional cases. And in this, we can imagine there are two similar processes in the convolutional calculation. The first should be is the so-called abstracting process. In this process, a convolution attempts to select or to select the neighbors of a center point, and that is similar to the neighbor weighting process in this solver. And the next, after selecting the neighbors, a convolution will try to extract or try to aggregate the information from these neighbors. That is a process similar to the normal estimation process in this solver. And since these two steps can correspond to each other, we can do some things by imitating or by tracking some similar process into this, such as in the abstracting process. We have the normal estimation calculation in the feature space, and in the grouping process, we select the neighbors of a certain center point, like the neighbor weighting process, and by imitating or by mimicking these two processes into the convolutional operation, we can do this. We can repeat this process and stack them together. And by doing this, the model our model can be built based on this repeated process, by abstracting and grouping. And in the next layer, we do the same things, by accepting the grouping results from the last layer. We do the abstracting and then fit the result to do the grouping for the next layer.
So a couple of questions before, like the explanation, it's a bit hard to follow if the notations are not clear. So I'm starting from the left side.
Yeah.
What is WJ tau?
Yeah, it is exactly like this. Yeah, the J should be the same.
What is the W?
Yeah, W is the weight of this
from the network.
Yeah, for example, some points we will in the calculation we will put them a very high importance. Yeah, we set the model, not we. Yeah, it is the model to set the high value, a large value of the W. Yeah, and
we don't. The network doesn't train W, right? W is a result of an inference time of calculation from the network, or is it a trainable weight parameter?
It will be optimized during the backpropagation, and this process grouping in this process by backpropagation we will or the model will optimize weight this W. Yeah,
it's an optimization parameter, that's why we need a differentiation. That's fine. What is SI of T? S is the surface, it's the A and B.
Yeah. Which XI do you mean?
Down below, just above the x-axis on the left side.
Yeah.
Normal estimation, 2 rows above this, there is a capital S underscore I, upper score T.
Yeah.
What is S?
S means the tangent surface, or means that is a local space-time surface. That is. Yeah.
It's defined by A and B.
Yes. Yeah, because by defining the coefficient of this tangent plane, we can define the S.
Yes. Okay. Now we're saying that this is having the S, all the P's, and the NI is equivalent to having the neighbor weighting. That part I couldn't follow. What does it mean exactly? Can we move? Can we move directly from one to the other in the opposite way? That's the idea?
Yeah.
Okay. Okay, yeah, this makes sense because it's the argmin here. And then we have all the ends. And the P's, that's fine. The ends, that's okay. How can we reconstruct WJ of tau from the left-hand side?
Yeah. From the left-hand side, and actually, this reconstruction process is calculated by the for example, by this equation indeed we have a closed form solution of this equation. Yeah, that is the so-called least square solution. Yeah, we can. Yeah, so it's quite simple. If we have a certain x and their tau here, and also this grouping process, the W is calculated from the
that's not that's I will ask exactly the opposite. If we have the green arrow going from normal estimation to neighbor weighting, it means we already have A and B calculated. We have all the points, but now we should somehow be able to figure out WJ tau. Yeah. It's not that we have WJ tau, we're calculating A and B. It's we have A and B, we're calculating WJ tau. Yeah. That direction for me isn't clear. How can we do that inference? Or maybe it's not doable, and then that's not an equivalent relation, normal estimation and neighbor weighting.
and which part is
The
unclear?
green arrow, if we have SI of t, PI of t, and NI of t,
Yeah.
how can we calculate WJ of tau?
Yeah, that is because for example here, by fitting just one plane, actually it is impossible to perfectly fit all of the points like this, so that we have the deviation in each fitting process. And in this we can see not all of the points are on this plane. Yeah, they have many outliers here. And by feeding this deviation, these deviations into a model or into a MLP or into something else, we can the model can get the W for the next step.
For the next step, not for this step. Yeah. It's always calculating for the next one. So that should be tau plus 1, I think, maybe, or if there is any notation of training there.
Yeah, but here means the Frings number in this. Yeah, the step means the layers in the number of a certain layer. Yeah, but what you said is correct. Yeah, they are not in the same layer. In this step, we do the grouping for the next layer, and in the next layer, we take the grouping and calculate the abstracting in the next layer. Yeah, that is a repeated process. This layer for the next layer is for the next layer, and
that's fine. Yeah. Another question: what is D of L, small d of L with the gray background? In the abstracting box, the top part, D of L.
Yeah.
What is this?
This one, it is a 1D convolution. Yeah, because this in this we have just talked about the physical domain process. Yeah, however, in the feature space, in each step, we need to do this alignment from the static part to the dynamic part. So the D here is to change some. We can view this as the encoder to change the static features to the dynamic domain. Yeah, that is a 1D convolution. Yeah, in practice.
1D convolution. Okay. So we do a one dimension convolution. We do splitting.
Yeah. And this HL is also another 1D convolution. We try to calculate the weight or try to estimate an optimal weight for the next layer. Yeah. And
one second, I'm still on the D. 1 second, abstracting. So we have a one-dimensional convolution looking over a vector from one dimension, convolving. What is the kernel size in that convolution?
The kernel size is it is a number we defined, but in our experiments, this 1D a good enough value should be the half of the dimension of this static feature.
So it means half the points in the static feature, basically.
No, it means the feature dimension in the point. For example, we have each layer of the feature of, for example, let's say 64 in a certain layer, and after the D, it will become like 32 dimensions. Yeah.
Okay. So I'm missing, how can it be a one-dimension convolution if we have, let's say, n points and each one has 64 features? We convolving basically each feature?
Yeah.
Or yeah.
Yeah. For this each maybe the so-called 1D convolution is typically or done in the temporal axis in the 2D domain. Yeah, but in the 3D,
in the temporal,
it is a very widely used tool to aggregate the information from this points. Yeah, because we can imagine in the point, in the 3D point, it's hard to take the so-called 2D convolutions. Yeah, because each point for each point, it is hard to define its 2D grid or the 3D grid. So
yeah.
the 2D convolution is very popular tool in modeling this. Yeah, that but we can take this as the black box, and that is just trying to change or trying to encode these features. Yeah.
So okay, we're encoding features. So we have features and we have time, and we're encoding the features while keeping the time.
Yeah.
Okay. If tau is in RC and then the split happens, what is the split?
Yeah. In this split process, and because in this splitting process we have so many points. Yeah. And it is enough to fit a 3D space. However, in the high dimensional space, we have 64 space dimension space in the feature domain. Typically, it at least needs 64 points to fit this plane. It is hard to do within a convolution. Typically, a convolution we can just take a very limited points. Yeah. By and to avoid this over determined not the underdetermined equation. We are trying to split them to make this, for example, on each group, we have a lower dimension, like the for example, a dimension in one group. In this case, we can fit this a-dimensional plane on a-dimensional surface. Use several points. Yeah. As long as the point number is larger than 8, we can fit it. Yeah, but if in a if we don't do the group, we don't do the splitting process, we will need many points to fit one.
What is C and what is D? C divided by D. What is C and what is D?
Yeah, the C means here, yeah, after the encoding process, the whole feature is C. Yeah.
The size of the entire feature space is C. Okay.
Yeah. And D is mean the group number is the D. Yeah, by split this feature in the into D groups. In each group, the feature dimension is C.
Okay, so basically D is the amount of output channels that we have.
Yeah, actually,
okay,
the process to reduce the dimension, to
us
enable us to use several points. Yeah.
Okay, so now we did that abstraction. We calculated the surface normal for D groups per point. And then once we have these D groups, we do the grouping part, which means HL of K, DI again, we do one-dimensional convolution, I guess, over the PIs, and then we get HLK, which is the result. It's all the features. This is not already in time. This is after time space, and then so the output of grouping is basically of size D as well. We have D outputs for grouping, right?
Yeah, the output of the grouping is the W here. Yeah.
Yeah.
And it is used for the next abstracting process. Yeah. The weight here. Yeah.
Yes.
Yeah, the abstracting is trying to calculate the A and B, and the grouping process is to calculate the W. Yeah.
Aha. And the grouping process does back propagation, or is it direct calculation for W?
Yeah, it is optimized via the back propagation. Yeah, but in its calculation process, we don't need the back propagation. But
okay,
we have the W. Yeah, the propagation can be used for the optimization of this. Yeah.
So we'll talk in the next slide. We'll talk about how is the W calculated.
Yeah.
Okay.
No, the calculation is finished. Yeah. Next slide. We would like to just talk about the whole structure. Yeah, because in this in the last slide, we only...
Okay, I understand. Okay, I understood. Yeah. But the calculation for W is basically made through that DL of Pj of tau, and that DL of Pj of tau is optimized with back propagation, basically.
Yeah.
Okay. Yeah, that makes sense. Now I see here below abstracting there is concatenate. So we are concatenating all the groups to one big feature again, to one big group with all the features, the 64, let's say.
Yeah.
Okay, and then C of L. What is C of L?
C of L. It is that because we can see, yeah, that is what we are talking about on the next.
That's that's just basically the output on the flow guided learning, model. Okay.
Yeah, that is so-called yeah, we can see here, yeah, because on this layer typically one gray, the gray parts are just trying to mimicking or trying to imitating the so-called
got it. Yeah.
However, how by after getting these features, we need to take this feature as the input and do the next step like the modeling. Yeah, the orange ones are the so-called modeling modules. Like, and the core idea is quite simple. Because all the CL here, all the concatenation, all the addiction operation here, and all of this are just to achieve one goal, that is to align the dimension to make this calculation feasible across different layers. Yeah, and that is and that's it.
Perfect. Okay.
Yeah. Thank you. Yeah, and that is almost all of our methodology part. Yeah, and if we have any question, we can ask here or after our talk. Yeah, it's so welcome. No problem. Yeah. And next, we will talk about the ablation studies. We see here on the last several steps, the last several slides. We talk about that how do we use the static or how do we use the temporal model to build to define our process. In the ablation studies, we try to prove three aspects. One is that how we actually get we actually benefit from the calculation or to benefit from the pre-trained weights of these static models. Yeah, because by extending this static model, we not only get the advantages from its well-developed structures or something else or ready-to-use codes. Also, the pre-trained weight from the static data can help to improve the performance in the dynamic task. That is the first aspect we're trying to we are trying to prove. Yeah, and indeed, yeah, it's useful. Yeah, it can improve the accuracy by about 2%. Yeah, the second aspect is the space the space time normals. Yeah, can indeed capture the dynamic information. Yeah, also we improved it, and the third part, it is the neighbor weighting process. Yeah, it's indeed helpful. Yeah, and yeah, and in this ablations, we are trying to prove we can get benefit from the static model, and also we can get benefits from the normal estimation and the neighbor weighting. Yeah, and that's all of these ablation studies. Yeah, and we also compare our model to the state of the arts.
Can we look at the ablation studies again?
Yeah, please.
So actually what we see here, that spatial static with pre-training without temporal has higher accuracy than the temporal, right? Like 0.1 and 0.4.
Yeah, but the best one should be we combine this the temporal and
yeah, of course, but then this gives a hint of saying, well, the pre-training is what's important. The temporal part is it's nice to have, but what making really the difference is pre-training based on this first part of the table. Or am I misreading something or misunderstanding?
No, actually, you have a very in-depth understanding of our work. Yeah, because we know here first for the static model, like the blue one, yeah, we can pre-train this static models used by using the static data set. Yeah, that is the first pre-training. And the second pre-training, the so-called on the temporal domain, we are trying to pre-train the static model like this, and that fit this because we can see here the dynamic model. The dynamic part is based on the static part. We can see these arrows. Yeah, that is calculated from the orange one, and the gray one is calculated from the from the blue one. So by pre-training, so the pre-train process of these blue ones is indeed helpful to the orange ones. Yeah, that is what we're trying to prove in the in this column. Yeah.
The pre-training, the temporal pre-train means we're only pre-training the orange part without the blue part?
No, it means we only pre-train the blue part. Yeah, but use the pre-training blue part to calculate the orange part. Yeah.
So I'm not following something. Can we go back to the table?
Yeah, back to this slide.
So we have a spatial static pre-training and we have temporal flow guided pre-training. And then if we look at row 5, we do both.
Yeah.
So what's the difference between spatial pre-training and temporal pre-training?
The differences would be here. If we do the temporal pre-training, yeah, or we can see that we don't take the we don't take the spatial pre-training or the temporal pre-training on the first and the third line.
But what part of the network do we pre-train when we do the temporal pre-training? Which way?
Temporal pre-training means we use the pre-train feature from the static model. Yeah, that is the so-called temporal pre-training. And we not just we not direct we don't directly pre-train the temporal model. Yeah, because that cannot be pre-trained by a static.
Because it's not static, of course. But then this is the same as static pre-training. There is no difference.
Yeah, that is no difference. But the differences would be we get the result from the blue one or from the orange one. Yeah, because if we don't have this, we don't have the temporal branch, or we don't have the spatial branch. Yeah, this minus here means that we don't use this branch. Yeah,
so basically, but what I'm trying to aim is, if we look back at the table, row 4 and row 5, the pre-training is exactly the same. There is no difference in the pre-training for spatial and temporal between the two rows.
In the outcome or in the result, in the final prediction, the differences, the differences occurs.
But the pre-training is the same?
Yeah. But the pre-training process is the same. Yeah, I agree with you.
Yeah. So if we look at the table,
process is all the output or the result or the we say prediction process is different.
Yeah, but between row 4 and 5, there is no difference in pre-training. There is only difference in the ST normal and weighted parts.
Yeah.
Basically, in row 4, we use both. In row 5, we don't.
Yeah.
But in row 5, accuracy grows, even though we do exactly the same pre-training and we omit some of the calculations of the network.
Yeah. It means that two streams are better than one. That is expectable. Yeah. Because the aggregation of both the static information and the dynamic information, we can imagine it should be better than using just only one of them.
But that's not what we see. But this is not
just what we see. Yeah, the third, we try to but in the fourth line, we try to remove the static parts, and in the fifth,
there is no static part.
Yeah.
So number 4 means there is no static part in the network at all.
Yeah. Right.
Oh, okay. This wasn't clear. So basically, row 1 and 2 mean we only use the static part once we pre-train, once we don't. Row 3 and 4 means we pre-train, but we don't have the static part of the network at all.
Yeah.
Okay, wasn't clear. Okay.
Yeah.
This makes more sense now.
The upper part is the case that we only use one stream, and on
Yeah.
the lower part, we use both of the streams. Yeah. Yeah, but these are both of the streams. Maybe we omit some modules in this calculation. Yeah.
Okay.
Okay.
Yeah, this makes sense.
Yeah. Let's see the next part of the gesture recognition. Oh, that is boring. We just trying to prove our model indeed outperforms the state of the art, and it's robust to the noisy background. And next is some visualizations here. We are trying to improve. We are trying to prove the fact that the appearance streams or the static streams is complementary to the motion streams. Yeah, they actually do the different things. The first one is trying to capture the appearance, and the second one is trying to capture the motion ones. Yeah, and the last slides of our work one is the quantitative results of the action classification. And in this part of the experiments, we are trying to prove, not only that our model not only surpasses the state of the art, but also it works well on the large scale data set and across different models. Yeah, like this, the green ones are the vanilla static models. The red ones are ours, and the orange ones are the state-of-the-art dynamic models, and the blue one are the raw two-stream parts. And we can see our models we have high accuracies, but with less parameters and less flops. Yeah, and that is the end of our talk about the work number one. Yeah, and any questions or comments?
No questions, no comments. I think all my questions were during. There were many. I apologize for all the extra questions. It took us a bit longer, but
your questions is very helpful for us to clarify every point of our model.
Yeah, very interesting work, Joshing. We have 4 minutes left. I don't know if we'll have time for the next part.
We can just skip the second work. Yeah. In this work, we are trying to bridge the gap between the weakly supervised detection problem and the fully supervised classification problem. But that is also use a very simple idea. We use this low confidence predictions and we use the high confidence predictions as the ground truth. Yeah, but this ground truth is not that reliable, and we use this unreliable unreliable high confidence ones to train the low confidence one in a fully supervised approach. And by doing this process, actually we are doing the detection task in the weakly supervised manner. Yeah, and that's all of core idea. Yeah, but if you have any of the audience have interest, yeah, please refer to my paper of the so-called graph convolutional label noise cleaner. Yeah. And And that's all of our two talks. Yeah, a perfect ending of our 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 lectures today.
Jishing, thank you a lot for giving this talk today.
Thank you, Peter. Yeah.
Also, we
Your
had to wake
invitation.
up earlier for this, so I appreciate it. Anybody who will watch this recording, feel free to comment on YouTube or on our Discord. We'll have Jishinka also. Also, I'll ping him if there are any questions, so people could follow up. And I think we could wrap it up. Thanks those who watched the recording. Thank you, Jishin, for coming. And this is, by the way, our last, anybody watching, this is our last talk, last recorded talk. So hopefully we'll have more in the future. Soon they're not expected more, but we'll see. Wish everybody a good day, a good week. And bye for now.
Yeah. Bye.